Alright, so we're going to talk about our inscribed figures and our three-dimensional rotations of these conic sections. So we start by thinking about quadratic systems as we start to look for solutions between these systems. And I can have an ellipse and a line, or parabola and a line, or hyperbola and a line. We have different things for solutions, but basically we're looking where the graphs cross, where they intersect. And we can think about it geometrically. They don't cross, there's no solution. This would be one solution. This gives me two solutions. And so algebraically, we would be able to solve it using what you did in algebra. And we can substitute in this case. So we have two equations, two variables. We can solve it. I substitute that for y, and then it's just algebra. I plug through and I try to figure out, isolate x. If I get something that's quadratic, then I'm going to have to use a quadratic formula or factor it or graph it. But again, once I get one variable, I can get the other and then go back from there. This one, in the case, I can factor out an x, and I get x is 0 or negative 4 as my solutions, my two solutions to that value. Again, this is a parabola, that's a line. I'm looking at this type of situation, except it crosses at two places, not in one. So that makes sense. If I got three solutions, that wouldn't make sense for the geometric interpretation. Right, that's the shape. And another one I can look at, again, is we take conics intersecting conics. Same process. Hopefully there's an easy substitution. I'm going to be able to get an x squared value and hopefully factor something out. And in this case, I'm able to factor and I can get my two values. If I was going to think about what we have here geometrically, that's going to be a hyperbola. This is going to be an ellipse, right? So it's something, we don't have a picture over here, but we can have our solutions as we move forward. So I get my y values, and we get our solutions to the equation. Right, so there's three, which again can make sense for if you have an ellipse and a hyperbola, what that would look like geometrically is possible. We might have a word problem where we have to determine the equations and then solve them. So if we have the sum of squares of two numbers is 45, that's x squared plus y squared is 45. The sum of the first number and the second number is 39. That's going to be x plus y squared is 39. That's a parabola. And then I just solve. So I solve for x, and I can plug that in there, and I would be able to do the algebra behind it. In other words, a circle and a parabola as intersect. The difference of the squares is 47. Again, that's going to be a hyperbola, and then the sum is 50. That's going to be a circle, and then again, I can solve by substitution and go from there. And hopefully that's not too overwhelming algebraically to try to get your numbers to work. And once you get a y value, you can get an x value. Don't forget your plus or minus on those as you're looking for more than one solution, and you get your values there. So you'd have four sets of solutions, four coordinates, right, as you move forward. So positive 1, positive 7, positive 1, negative 7, negative 1, positive 7, negative 1, negative 7. Alright. Another application of this would be if we're inscribing a figure in a quadratic surface. So these ones look a little bit confusing to start with. But we have a rectangle inscribed in a parabola given an equation, and it's bounded by the x-axis and extends upward to the vertex of the parabola. And we want to write the equation, and then we're going to find a maximum area of the rectangle as well. So the way we can go about this is, first off, by making a picture that makes sense. So we have a rectangle, we have a graph for our parabola, that's our parabola, and then we have a rectangle that's embedded in there, and we don't know the size of it. That's just an approximation at this point. We're looking for one that's a maximum value, and then what we're going to do is try to figure out which one is best. That's what we're trying to find out. So we take a general case, right? That's some value x is 0, and I need to figure out the y value. Well, the y value is given by the equation on the parabola. So whatever x is, you plug it in here and you get y. And so that's going to be a key part here, because now I have something that's just in terms of x, which is going to allow me to maximize it. So if you think about our actual dimensions, This is x and x, so that's 2x. This is negative x squared plus 9. To find the area of a rectangle, you take the length times the width. And in this case, that's going to be our equation here. So we get some value, right, that we can then plot on our calculator and try to make sense of what's happening to it. You got to be a little bit careful. This is a cubic, right? And you only have certain things that make sense. This function doesn't know that it's within this parabola. So the largest value that you could ever make would be x equals 3. At that point, you would have basically a line. You'd be outside of your parabola, so you can't go further out here. So you have to tell the calculator and bound the x values. I can be between 0 and 3. That's the only thing that makes sense. I'm looking for the maximum value on that range, on that interval. We can also start to look in 3 dimensions as these things would rotate and what those figures would look like. So those are our hyperboloids, paraboloids. But let's say that we have to be able to graph these to begin with. So we start with a hyperbola and sketch a graph. And in this case, our center is easy and our asymptotes are easy. And then what we're going to do is we're rotating it around the y-axis from 0 to 3. So we're going to rotate it around this axis, and we're only going to worry about these values in that range. So what that would look like would be that type of kind of almost cylinder, but not a cylinder because the sides are curved in accordance with the hyperbola. But that's kind of our process. Same idea with a paraboloid. So if I have a parabola, I need to make a sketch of it, which means I'm going to find the vertex, and I'm going to determine which way it goes. So it's a y-squared value. I'm going to have a vertical directrix where I add p to it, and that's going to be my focus. And then as I rotate that around the x-axis, I get this bowl-shaped figure, and I only stop at -4 because it's bounded this way, but I get that bowl-shaped figure that's pointing to the left. Alright, we can do the same thing that we did before with the rectangle, except do it in 3 dimensions and look at something like a cylinder. But the equation of a cylinder is within a paraboloid, and it's created by rotating this parabola from this equation. Y squared is -4, x minus 4 from these values. We want to write an equation of the volume in terms of a point located on the paraboloid in the first quadrant. So the way this is going to work, I have a center. There's my center point, and then that's my p value. P is -1. That means I'm going to subtract 1 from that. It's a y squared value, so it's going to open up left and right. In this case, it's going to open up to the left, and then I'm going to rotate that thing to get my paraboloid. So I get my y-intercepts, and that becomes my paraboloid. And what we're going to do is we're going to embed a cylinder in there, and we take a general location on point xy. So there's my cylinder, and I have to somehow get that in terms of variables that I can then maximize. So if I look at that, my x value, right, and then I have an r value. So x will be x. R is again dependent on where I am on the parabola. In this case, the rotation doesn't really matter for 3 dimensions. I just want that y value. So I use my equation, right, where my y value just plugs in there. That's my y value, and we take our square root, right, because this is a y squared value. So I plug in my y value, and then it's just trying to figure out my volume formula for a cylinder, which is going to be base area times height. So my volume becomes pi r squared times height, where r is that y value. When I square it, I'm going to get just the y value, y squared back, and that becomes x. And so again, I'm getting an equation with just x in it, and I have something at this point that I can maximize with the calculator and get the basically length of the maximum cylinder within that paraboloid.